All right, so what we have here are improper integrals, something we haven't done yet. Up to this point, we have required that definite integrals satisfy two properties. First off, the domain of the limit of integration is finite, and the range of the integral must be finite on our limits of integration. Whether you really absolutely knew that or not, we did that, right? So what happens if we're looking at something like what we have down there, where integrals that aren't satisfying this, we're going to call them improper integrals. But take a look at this one. Look at our limits of integration on that. From 1 to infinity. Huh? Not necessarily. They may diverge, they may blow up, they may not. They may actually converge to an answer. And so we're going to take a look at that. What to do if they do converge, how do you actually find that integral? And then, of course, if they diverge and stuff like that. So we have the version on the top where this keeps going in asymptotes towards the x-axis. And then we have the one on the bottom where it's asymptoting towards the y-axis as we go to 0. Okay? So let's take a look and see how we do this. So with infinite limits of integration, we are looking for what's the area that lies below it. So let's take a look here at this example. We've got integral from 0 to infinity of e to the negative x over 2 dx. So what we can do is say, what we want to do is find the area not from 0 to infinity, but from 0 to b, right? And we can call this the area out to b, okay? And we'll do e to the negative x over 2 dx. And when we do this, we can actually take this integral, negative 2e to the negative x over 2, and that's evaluated from 0 to b. And then that becomes negative 2 times e to the negative b over 2 minus e to the 0. And that gives us negative 2e to the negative b over 2 plus 2. E to the 0 is 1. So negative 1 times negative 2 is that plus 2. And then what we can do to get our original integral is we can take the limit as b goes to infinity of this different version we've done here, which will be our limit as b goes to infinity of negative 2e to the negative b over 2 plus 2. As b goes to infinity, e to the negative infinity is what? Goes to 0. And so this ends up equaling 0 plus 2, or just 2. So as we go to infinity, our area does approach to 2. Converges to 2 there. I mean, no matter where we stop, we're going to be slightly less than 2, but the further we go and keep going, we're going to get closer and closer to 2. It's like our area underneath asymptotes to 2, right? Okay, at least that's the way I think of it. So how do we do this? So integrals with infinite limits of integration are improper integrals of type 1. If f of x is continuous on a out to infinity, the integral from a to infinity is that where we replace infinity with b and then take the limit as b goes to infinity. You'll find that as you do more of these, you'll probably stop always writing out the limit and you'll just leave it from like a to infinity and stuff. But If we're going to negative infinity, same sort of thing. If it's continuous on there, we just go and take the limit as it goes to negative infinity. And of course, if it's negative infinity to positive infinity, then we just split it up into two integrals. One from negative infinity to some point, see, like usually you want to do something simple, like 0 or something, and then do the other one from 0 out to infinity. Especially if it's an even function and you have symmetry on both sides, then you really only have to do one of them, right? And double it. Okay, so just do that, take the limit. In each case, if the limit exists and is finite, we say the improper integral converges. We already know that. And the limit has, and that the limit is the value of the improper integral. If the limit fails to exist, the improper integral diverges, like trying to find the area underneath x squared from 0 to infinity. That would diverge. That would blow up. Okay, so let's take a look here. We've got this example over here. All right, so is that area under the curve in y equals the natural log of x over x squared from x equals 1 to infinity finite? If so, what is its value? So let's take a look. So we're going to integral 1 to infinity natural log of x over x squared dx. And so we can say a, b, we're going to replace this, make this 1 to b of natural log of x over x squared dx. And here we can use substitution here. Anybody want to tell me what substitution they'd do? U equals ln of x. Okay. U equals ln of x. That means du is 1 over x dx. And I shouldn't say substitution, I should say by parts, sorry. I said the wrong thing. And then dv will be dx over x squared. And so v ends up being negative x to the negative 1. Sorry, I said the wrong thing. Okay. And then we can start substituting back in. We get equals, and we'll have negative natural log of x over x from 1 to b minus integral 1 to b, right? So we did u times v, and now we need v du. So we need negative 1 over x and 1 over x dx, like that. And so we get, I'm just going to leave this negative natural log of x over x from 1 to b. And then this integral becomes positive 1 over x squared, and 1 over x squared integrates to negative 1 over x. So minus 1 over x. And that one is evaluated from 1 to b as well, which means we can start plugging this in. We've got negative natural log of b over b minus natural log of 1 over 1 minus 1 over b minus 1 over 1. And then that gives us negative natural log of b over b minus, what's the natural log of 1? 0. So this is going to go to 0. So 0, so minus 1 over b plus 1. And now we need to take our limit. So we do limit as b goes to infinity of negative natural log of b over b minus 1 over b plus 1. And so we can do the limit of 1 over b pretty easily. What's that? Yep, that's going to be 0. And the limit of 1 is just 1, right? But we still have this limit as b goes to infinity of negative natural log of b over b. We still have that one. And if we look at that one, what happens? What's the limit of the natural log of b as b goes to infinity? No. No. Blows up, right? All right, it blows up because that minus sign, right, it moves up into that exponent. So our limit there is infinity over infinity, right? So limit b goes to infinity of negative natural log of b over b. That goes to infinity over infinity. So what do we do if we have a form like that? Yeah. So, and we do that by doing what? Yep. And so what's the derivative of negative natural log of b? And then what's the derivative of b? We still have that plus 1 we have to carry along. So we end up with just negative 1 over b. As b goes to infinity, what is that? 0. So that's going to go to 0, and we're going to be left with 1. There we go. Any questions on that? Okay. Yeah, shouldn't be too bad, right? All right. Try this one. A little hint for you, if you want to make it a little shorter. Huh? It's even. And double it. You could do 0 to infinity and then also do negative infinity to 0, and you'll get the same answer with time and add them together, or just do one of them and double it. the first things I always check whenever I see something that's a fraction with a something plus a something squared down there in the bottom is I start thinking of the trigonometric ones. Kind of looks Pythagorean theorem-ish. What's up? And so you can, I think it's probably, is it in the integral table, this one? How do you? Well, it depends on what the trig function is, doesn't it? Well, can you draw me what that inverse or arctangent is? I guess since I just told you what the integral was. Probably want to look at that picture of it. Can you draw a tangent function and then mirror image it across the y equals x line? Did you get the graph? So what is what's tangent look like? From what is this here? And what's this? And so if I want the inverse function, I look at that and I simply flip it around it. So what does this one look like? It looks like that. Right? Anybody get it yet? Got one answer of pi. Anybody else? Not you. Anybody else? What's this integral equal? I think we should know based on what I was just drawing out there. But what is a 1 over 1 plus x squared integral? Okay. Oh, you better not need that for those arctangents, especially since I have the graph drawn right there in green. Huh? Like pi, T-O-O. Not 2. Not TWO, right? Okay. So what's the arctangent of 0? 0. So that's a 0. And so now we need limit b goes to infinity of 2 times the arctangent of b. And looking at my graph over there, what does the arctangent go to as b goes to infinity? Huh? Had you done this middle version where we did negative infinity to 0, you would end up with 0, because if you look at it, the arctangent goes to negative pi over 2. You would end up with 0 minus negative pi over 2. So that one would have been pi over 2 as well. And then it would have just been pi over 2 plus pi over 2. Okay. Any questions on that one? All right. On this next one, I want you to see page, you're going to do this one on your own. I'll tell you the answer. But from 1 to infinity, this is a good one to know, of dx over x to the p. This is going to equal 1 over p minus 1 whenever p is greater than 1. And it's going to go to infinity whenever p is less than or equal to 1. There is a, see the text for this one, for the proof, and it's, I believe, on page 511. But you're going to want to know this. All right, tuck that one in your math tool belt. So what values of p does it converge when p is greater than 1? So like 1 over x squared, 1 over x to the 10th, it's going to work. 1 over x? Nope. Which I have a hard time with, I guess, because it sure looks like it would, doesn't it? 1 over x going down to 0. I feel like that one should be on the converge side, but it's not. That's the thing that kind of bothers me about this Calc 2 stuff, is ones like that situation just aren't very intuitive to me. Maybe it's intuitive to someone. I mean, I've done it out. I've seen that it does mathematically, but looking at it, like normally when I think of limits, I'm like, I want to zoom out and look and see, oh yeah, that's going to this. No, doesn't work. I don't know. Okay, I don't get that. Some of this stuff. Okay, integrands with vertical asymptotes. Okay. So what is the area of this region that lies under the curve y equals 1 over the square root of x from x equals 0 to x equals 1? So if we go to do this one, we can say 0 to 1 dx over the square root of x. We have a vertical asymptote, right? This is VA, vertical asymptote, at x equals 0. And so that's in our limits of integration. So come down here, a of a, and we'll do an integral of a to 1 dx over the square root of x, and then we're going to let a go to 0 from the positive side. 0 plus. Remember the left and right limits. So our integral here is integral a to 1 of x to the negative 1/2 dx, which should be 2 times the square root of x from a to 1, which will be 2 times square root of 1, oops, minus square root of a. And then we can take this limit, right? This is 2 root 1, 2 root 1. This is 2. Root 1 is just 1. 2 minus 2 root a. And then we can do our limit as a goes to 0 plus of 2 minus 2 root a, which is 2 minus 2 root 0, which is 2. Okay. Make sense? Or at least can be done. Not sure if it makes sense or not. Well, I mean, you have to remember, we're not really saying, I feel like we're not really saying the area, we're saying the area converges to this. Like, this is what it approaches as we keep getting closer and closer to 0. Technically, with this graph, we never get to 0, which, again, in and of itself is, I think, not, at least not by me, necessarily understandable. We just keep getting closer and closer and closer and closer without ever getting there. So, you know, I don't know. Does that work or not? So you have to be kind of careful with your language, right? We say that is what the area is. It just seems to approach to it. You know what I mean? Like, infinity is an idea. It's not like a concrete number thing we have. All right, so definition. Integrals of functions that become infinite at a point within the integral of integration are improper integrals of type 2. If f of x is continuous on not inclusive of a to b and discontinuous at a, then the integral of f of x from a to b dx is the limit as c goes to a plus from c to b. Okay? Just like we did right above there. And then if it's the other way around, if we're getting a vertical asymptote in the upper limit of integration, then we're going from a to b, and we're taking the limit as b goes from the minus side. All right, you see that? One is plus side, one is minus side. And then the third one is if it's discontinuous at c, where c is between a and b, then we're essentially going to split it into one that goes to c from the left and one that goes to c from the right. So you're putting together rules, the versions 1 and 2 up there. In each case, if the limit exists and is finite, we say the integral improper, it converges, and that the limit is the value of the improper integral. If the limit does not exist, the integral diverges and we're done. Okay, any questions? All right, let's investigate this one. Investigate the convergence of 1 over 1 minus x integrated from 0 to 1. Okay. A of b is our integral from 0 to b, right? Because we're asymptoting at 1. Of dx over 1 minus x. And then we'll let b go to 1 from the negative side. And so what's my integral of 1 over 1 minus x? Try again. If it was 1 over x minus 1, then it would just be ln of x minus, or sorry, it'd be ln of x minus 1, yeah. Negative. There we go. Because if we do the u substitution, right, we're going to end up with a -1 being added on, right? Because it'll be u equals 1 minus x, and then du is just -1. So du equals negative dx. So then we get negative don't forget that negative, ln of 1 minus x, and we're evaluating that from 0 to b. All right, and then we get negative of, I'm just gonna bring that negative all the way out front. So this will be, or maybe I won't, it's just minus ln of 1 minus b plus, right, minus ln of 1 minus 0, which is just going to be what? 0, because it'll be just the natural log of 1, which is just going to be, so that's going to go to 0. And now we need to do our limit as b goes to 1 from the minus side. And when we do that, what happens here? We end up with what? We end up with the natural log of 0. And what is that?
Natural log of 0 would be 0.
So natural log of 0 equals something. That means e to the x has to equal 0. It's not undefined, but it's going to an infinity, isn't it? A negative one there. E to the negative infinity, 1 over e to the infinity, right? So maybe I could write this out a little more. Let's see if we can make this. Let's see. This is what I did before to explain. This is, we can make this negative natural log of negative b plus 1. And then that can be negative natural log of negative b plus b minus 1, sorry. And so we're still going back to it. I'm not sure if that helps see it at all or not, but anyway, this thing, when we take our limit of negative of absolute value of 1 minus b, that natural log is going to go to negative infinity. So this is negative of negative infinity, which is infinity. And so therefore, what? Good. Which is again strange to me because why? I don't know. I can't picture why one looks very similar. They're both asymptoting. One's blowing up. I mean, I can do all this math, but picturing it in my head just doesn't compute. My intuition is totally wrong here. And I've never been able to come up with a way to fix my intuition on these. So if you come up with a way, please let me know. You come up with a way to picture this. So, all right, any questions on that one? Okay, how about this one? So what I'm going to do is leave this one for you to try. It's not too hard. You just go from, you're going from 0 to 3. So you have to go from 0 to 1 and then 1 to 3, right? You got to split this up, right? Because of that. So give that one a try. And you should equal 3 plus 3 cube root of 2. So this one, converges. But try that one. There's what your answer should be. Split it up into two things and try it. One from 0 to 1, or yeah, 0 to 1, and so So in other words, integral 0 to 1 dx over x minus 1 to the 2/3 plus integral 1 to 3 dx over x minus 1 to the 2/3. So do both of those. And then take our limit as we approach. So it'd be from like 0 to b and take the limit as we approach from the negative side. And then from, you know, b to whatever, and take the limit as we approach from the left side, the right side, and the positive side. Okay? Try that one and see what you get there. You should get that answer. Okay? Tests for convergence and divergence. When we cannot evaluate an improper integral directly, we try to determine whether it converges or diverges. If the integral diverges, that's the end of the story. You're done. If it converges, we can evaluate it or approximate it, you know, do like the computational versions or something like that, right? So we want to know, we basically want to be able to figure this out so just we know if it's even worth trying to figure out, right? So first thing, does the integral, oops, I probably could write this in. And this doesn't necessarily have to be for ones that we, you know, that we cannot directly do, but ones even that might be hard because you don't want to sit there and waste your, you know, an hour doing an integral just to find out it diverged, right? So it may be worth it to you to check if it's a difficult integral. So let's look at this. Does the integral 1 to infinity of e to the negative x squared dx converge? So we need to figure that out. We don't have a good elementary integral formula for that. So let's look at the following. If we compare that to just e to the negative x, and you can see e to the negative x in the graph. You can see the e to the negative x is the red one, and the e to the negative x squared is the blue one. And what can you see as we go to infinity is always true as soon as we get from one on. What is always true about e to the negative x compared to e to the negative x squared? But what about the comparison of the two? From here over, what is true of e to the x compared to e to the negative x squared? You're just telling me something they both do. What's a comparison of the two? Like if I said, what's the comparison of 7 and 3? 7 is greater than 3. So e to the negative x is always greater than e to the negative x squared from 1 to infinity. There we go. We'll get there. So from 1 to infinity, e to the negative x is greater than or equal to e to the negative x squared. Okay, that means our integral from 1 to b of e to the negative x squared dx, how is that one going to compare to an integral of 1 to b of e to the negative x dx? What? Which is smaller? Is less than or equal to? Right, they're equal at 1, so less than or equal to that. So if e to the negative x converges, what does that mean about e to the negative x squared? Converges. Think of the pinching theorem. Remember the pinching theorem? Oh, yeah. Right? So there's no way e to the negative x squared can diverge if it's always underneath e to the negative x and e to the negative x converges, right? Now, if e to the negative x diverges, then we don't know. it may or may not, you know what I mean? Like e to the negative x squared may still diverge or may still converge. It won't tell us. But if we can show that e to the negative x converges, then we know the other one has to as well because it stays below it the whole way. It's always less than it. So e to the negative x, if we start integrating it, it's negative e to the negative x from 1 to b, which is negative e to the negative b plus e to the negative 1, right? And so we then can input e to the negative infinity. What's that going to be? 0. And so then we end up with just, when we actually take that limit, right? Limit of b goes to infinity of negative e to the negative b plus e to the negative 1. That's 0, right? And so we end up with just e to the negative 1. So it's converging, right? So it converges. And we therefore know that the other one also converges. Do we know what it converges to? We have no idea what it converges to. We just know that it does. Okay? Don't know what it is. Okay? But we know it converges, so therefore it would be worth actually doing the integral somehow. All right. So here's our theorem. Direct comparison test. Let f and g be continuous on a to infinity with g of x being greater than f of x being greater than 0 for all x greater than or equal to a. Then if the integral of g of x dx converges, then the integral f of x from a to infinity also converges. If the f of x one, the smaller one, diverges, then the other one also has to diverge. If the larger one diverges, then we don't know if the smaller one diverges or converges. But if the smaller one diverges, then the larger one must also diverge. Okay, so we only have these two situations where it helps us. Okay. All right. I think we'll do these examples tomorrow. And then the last thing, just take a look at this so we can, here, we have another comparison test. If we have the positive functions f and g and are continuous on a to infinity, and the ratio or a fraction of these two things, these two functions, converges to a limit L, then they either both converge or both diverge. So take your time and think about that one between now and tomorrow. And tomorrow we'll go through and finish those last examples, which I don't know if I'll record in the video or not, but you can look in the notes to find. And then we'll do this last example too, and then answer any questions. Okay? So that's it, guys. Thank you.